Alright, welcome back everybody. In this video we're going to look at the first couple of examples from the Revisiting Particle Motion lesson. Now remember, back when we studied derivatives, we talked about the relationships between various values related to the motion of something along a line. The relationship that if we knew position and we took the derivative of the position function with respect to time, we would end up with a function representing velocity. And if we took the derivative of the velocity function with respect to time, we ended up with acceleration. And we also looked at the fact that speed was the absolute value of the velocity function. Well, now that we have integrals involved, instead of just moving from position to velocity to acceleration, we can move backwards up the hierarchy. If we know the acceleration function, we can use the integral to find the velocity function. And if we know the velocity function, we can use the integral to find the position or displacement of a particle, or, well, anything in motion along a line. So now that we have the integral, it widens up our ability to answer questions related to particle motion. And you might want to take a few seconds and read through the text that you saw on all these different things. But we're going to break right into the examples. We'll look at example 1. A particle is moving along the x-axis with velocity modeled by the equation v of t equals t squared minus 3t plus 2 for time from 0 to 6. At time equals 0, the particle has position x equals 8. Where is the particle at time t equals 5? And then a second question, what is the total distance traveled by the particle during the first 5 seconds of motion? So let's start with, where is the particle at time t equals 5? In order to find out where the particle is at time t equals 5, we need to consider where it was to start with, and then in order to find its displacement, we're just going to integrate the velocity function over that interval. And that's going to take into account all the different changes in direction that might happen with that velocity. It's going to take into account really everything as far as the displacement goes. So in order to find the position at time 5, we're going to take the position, we're going to take the position where we know it, in this case at time 0, plus the integral of the velocity function over that time interval. And now we can just go ahead and calculate that. It's going to be the position at 5. It's going to be the position at 0, which we're told is 8. And then we need to just take the antiderivative and find this integral. So we've got 1/3 t to the third minus 3/2 t squared plus 2t, which we're going to evaluate from 0 to 5. And we'll go ahead and calculate that. And so we've got 125 over 3 minus 75 over 2 plus 10 minus 0 plus 0. It's nice when one of those limits of integration is 0 and leads to all those zeros in our calculation. And so we'll go ahead and calculate that. And we've got 8 plus 125 over 3 minus 75 over 2 plus 10. And the position at 5 is 22.16 repeating. Okay. Now, I also had the alternative at this point when I wrote this, and it really depends on whether you have a calculator in your hand or not, whether it's a calculator section or not, but I could have opted to just go ahead and take that integral numerically if I'm working on a calculator section of my AP exam, for instance. And in fact, that's the advisable approach if you're working on a calculator section. for time purposes. Instead of taking the antiderivative by hand and evaluating, a lot of times it's better for us to just go ahead and use the calculator if we're working on a calculator section. All right. The second thing we're asked here, what's the total distance traveled by the particle during the first 5 seconds of motion? To find total distance, we're really talking about the integral of speed instead of velocity, because to calculate total distance, we'll calculate all the distance that's traveled in a positive direction and all the distance that's traveled in a negative direction, and we'll subtract away all that distance that's traveled in a negative direction to come up with the total distance traveled. So really, distance traveled is the integral of the speed function. Displacement is the integral of the velocity function. So to answer this second question, we are just going to take the integral from 0 to 5 of the absolute value of this. And I could go through and find out where the particle changes direction on that time interval, but I really don't need to. If I have a calculator in my hand, I can just go ahead and use the numerical integral function for the speed. And it might take a few seconds for my calculator to handle this, but when it's all done, this is going to give me the total distance traveled. And the total distance traveled was 14.5 units. Again, like I said, I could have figured out where the particle changed directions and split this into 2 integrands and done it by hand. It's just a lot quicker in this case to go ahead and just handle it with the integral of the absolute value. All right. Let's go on to example 2. In the box here you see something that I've found has been pretty important on recent AP exams. They talk to you frequently about when speed is increasing or decreasing. Speed is always increasing when the signs of the velocity and the acceleration are the same. If we have positive velocity with positive acceleration, that means speed is increasing. If we have negative velocity with negative acceleration, that means speed is increasing. And then the second part, speed decreases here if the signs of velocity and acceleration are different. If velocity is positive, but acceleration is negative, that means that the speed is decreasing. And conversely, if velocity is negative, but the acceleration is positive, that also means that the speed is decreasing. Alright, let's look at example 2 here. This is a free response question number 4 from the 2003 AP Calc AB exam Form B. This is a non-calculator question, or at least it was on the exam. So let's handle it without a calculator. A particle moves along the x-axis with velocity at time t greater than or equal to 0, given by v of t equals -1 plus e to the 1 minus t. Okay, first, find the acceleration of the particle at time 3. So we're looking for the acceleration at time 3. That's going to be the derivative of the velocity function, which is negative. Let's find the acceleration function first. The derivative of the velocity function, which is negative e to the 1 minus t. And so the acceleration at time 3 is going to be equal to negative e to the 1 minus 3, or negative 1 over e squared. That's the acceleration. Part B. Is the speed of the particle increasing at time t equals 3? Now here we're going to use what we just talked about in the box above. We already know from part A that the acceleration is negative. So now we need to determine, is the velocity positive or negative at 3? The velocity at 3 is equal to -1 plus e to the -2. And that is less than 0, because 1 over e squared is less than 1. So since the velocity is negative, we now have a negative acceleration and a negative velocity. So the speed is increasing because both velocity and acceleration are negative. On to part C. Find all values of t at which the particle changes direction. Justify your answer. We've previously discussed, when we were talking about derivatives, that the particle changes direction when velocity is equal to 0. So we go ahead and set the velocity function equal to 0 and solve for t. So we've got 1 equals e to the 1 minus t. Taking the natural log of both sides, natural log of 1 is 0. And the natural log of e to the 1 minus t is just 1 minus t. And so we find t equals 1. Okay. Justify your answer. So now I want to look at this particular spot here. In justifying my answer, it's at t equals 1 because velocity changes from positive to negative there. Yeah, changes from positive to negative there. Darn stylus. And then part D, find the total distance traveled by the particle over the time interval from 0 to 3. Now, they were nice enough here, since this is a non-calculator question, they had us already figure out where it changed direction in part C. So for part D, to find the total distance traveled, we're going to take the integral from 0 to 1 of the velocity function, which was negative 1 plus e to the 1 minus t. And we're going to take the integral from 1 to 3 of negative 1 plus e to the 1 minus t dt. And which one are we going to subtract? Well, when is the velocity negative? The velocity is negative below the axis, so we want to subtract that one away. Alright, and then we just need to go ahead and find our antiderivative here, which is going to be negative t minus e to the 1 minus t, which we're going to evaluate from 0 to 1, and we're also going to evaluate it from 1 to 3. Okay, and so we've got negative 1 minus e to the 0 minus 0 minus e minus quantity negative 3 minus e to the negative 2 minus negative 1 minus e to the 0. And if we calculate all this stuff out, we've got minus 1 plus e minus 3 minus 1 over e squared plus 2. So we've got negative 2 plus e minus negative 1 minus 1 over e squared. And so we end up with the total distance traveled being negative 1 plus e plus 1 over e squared. Alright, that's the end of example 2 here, and that's going to be the end of this video. We'll come back in the next video and handle examples 3 and 4 from this lesson. See you guys next time. Have a great rest of your day.